Welcome, and a very warm welcome back to the third lecture in the series of presentations based around the media project, cyber attack, cyber crime, cyber warfare, and cyber complacency. As I say, this is presentation 3. We'll be dealing with a deep dive into DNS-reflected attacks. There'll be some packet traces, and there'll be some gentle overviews for those that aren't so interested in the deep technical mix that we'll be going into. So what exactly is this project about? Well, it's a multimedia project. I've tried to embrace all forms of media, hence the presentation, the book that you see before you, example code for exploits, mitigations, labs, all provided on the internet. And that the reason d'etre for that is twofold. Firstly, in the UK, far more acute than the States, in the UK and to an extent Europe, the risk of cyber attack is great and the exposure is even greater. Particularly in the fact that all the money that is invested, all the initiatives, and it is quite diminutive, quite small, as you will see, is either for an offensive force or to protect the status quo. Now that's all well and good. I have no problem, but when the attack comes, we will have little use for government procurement websites or the House of Commons websites. We are exposed, and when the time comes, the people need to be aware that if things go on as they're going, these websites may well be up, but the gas, the electric, and the banking system will all be vulnerable and all turned off. And it's not scaremongering, it's about realigning our priorities. Secondly, and a little personally, many books and projects such as this are done for self-adulation, self-promotion. Hopefully that's not true in this case. I recently, and I'll share with you some personal details here, suffered a catastrophic and chronic medical condition, an industrial injury if you like. And the effect, as I say, was profound. And it was based very simply around sepsis, blood poisoning. And I became aware that although 37,000 people a year die from sepsis, which is greater than most cancers, there is almost no support and, frighteningly, very little awareness amongst not even laymen, but more worryingly amongst the medical profession. So all the net proceeds from the book will go towards the charities that will help people in the future overcome some of these horrific after effects. Now, enough of the heavy stuff. Let's go and do the deep dive on attacks, but we'll start slowly with some basic concepts and strategies. Now then, we know that botnets can launch DDoS attacks. But what kind of attacks can they really launch? The first of these is the basic flow attack. These basically are packets, often not even compliant to the protocol of the port they're being sent to. The objective is just to use up bandwidth. Moving up the evolutionary scale, we get more complex packet floods. These consume an atypical amount of resource, and the best example, and still the most common attack you're likely to see, is the SIM flood. Still at the infrastructure level, but very much more cognizant of protocol types and how the independencies of the internet are held together, we have reflected amplified floods. And the most trendy, shall I say, because it's not necessarily the most common, but the most trendy you're most likely to see is a DNS, reflected and amplified attack. Now, we've written some example code that in a future presentation we will provide packet traces, analyze exactly how this works, and why maybe it's not quite the threat that it's suggested that it is. And lastly, we have the application flood. This is where the attacker has crafted the attack in context of the system that is being attacked. The attacker knows that it's an authenticated website and that maybe the thing that's most likely to be resource exhausted or page locked is the authentication mechanism. Database page locks, application throughput, all sorts of key resource restraints come into play with these attacks. From the previous slides you have learned that there is an attack hierarchy, starting at the most basic with the basic floods, moving on to the complex flood that you learnt in the last presentation, through reflected and amplified attacks, right up to the top of the food chain, which we'll see in another presentation, the application level attack. But you will recall, will you not, that this presentation is about the reflected and amplified attack. Now, I know you think I'm an old cynic, but I do believe we tend to give attack types and protection methods quite grandiose names in security, often not backed by scientific evidence or diligence. There are basically two strategies for amplification, and one is becoming more emergent, a fairly recent introduction. If we look at the typical, what I'd call normal types of amplification, it usually works with one agent sending a packet which is amplified, as you can see here represented by a bullhorn. And in this case, the multiplication factor is the packet numbers. One packet goes in and multiple packets come out. They tend to be of the same size. So that would be true of the directed broadcast attack or the charge-in type attack. A newer type of attack, and one we're going to look at later, is where the multiplication isn't done by packet numbers. In this attack, the threat agent sends a packet of a set size and a similar number, often slightly more, number of packets emerge from the amplification technique. However, these packets are much, much bigger. So the amplification occurs in the terms of number of bytes, not necessarily in terms of number of packets. And this is true of the DNS reflected attack. Now, as you'll guess, the other half of an amplified reflected attack is reflection. Mirror, mirror on the wall, who is the baddest attacker of them all? Reflection simply means you bounce packets off either another server or another application. It's as simple as that. Now here we see a representation of a reflection attack. There are three parties involved. We've got the attacking computers, we have the victim computers, the people that are going to be attacked, but also we have a collection of servers here we've called the mirror.com where the attack is going to be bounced off of. Now in this attack, read reflection as spoofing, because that's the key. Usually the attacks are UDP based because they're easily spoofed, and in this case we're spoofing the source address. We're using a simple payload, just a collection of A's, very similar to the previous payload we saw on the last presentation that you will remember as just a string of nearly 8Ks of H's. In this case we've used A just to make a change, and when the attack is launched you'll see that the SADRA, the source IP address, is not 172.16.0.1 as you would expect. Actually it is 192.168.0.1, the address of victim.com. The destination address is mirror.com, 10.0.0.1. So what effectively happens is that BadBot sends a packet to the reflection server, mirror.com, that when it responds, the packet doesn't go back to BadBot, it goes off to victim. And that's how the reflection occurs. It is simple source address spoofing. Now it's time to put together all the learnings you know. You understand reflection, you understand amplification. I know you will agree it is very simple. As always, there will be an attacker, and this attacker will be a member of a botnet. He will fire a spoofed UDP packet that contains a DNS query to a name server. This name server is not the authoritative name server for the domain that is being queried, so the name server will have to query the authoritative name server, in this case loud fat bloke. Once the cache is populated, and I know you know this, it will respond to the victim server because the original bot spoofed the IP address. The amplification will occur in the number of bytes. So if we play the slide, you can see the any query for domain loud fat bloke. It was a recursive request, so mirror.com will have to query the authoritative name server for loud fat bloke, and then it will respond with a much bigger packet, and in this case the amplification is 47 bytes for the initiating packet, the query, whilst the response works out at about 300 bytes. So an approximate multiplication here of 6 times. So let's look at some real life code. DNS SP query.c that we wrote specially for this project. We have placed it publicly available on Packetstorm. The URL is shown below, and we have purposely written it, well, in fact I've purposely written it in raw C using socket code, so that you don't need to understand any complex Perl or Python libraries. What you see is what you get. It should compile on any Linux system that has the pcaplib installed, so that you can use it to experiment and test the concept. So let's start by looking at some of my C code. Why did we do C code? Well, many of the solutions out there, many of the examples on the repositories out there use complex libraries that most people won't understand, or they were written in Perl that kind of obfuscated the complexity a bit. It's amazing how many of these new languages like Python and some of the Perl languages can just do something quite complex with one statement, and that kind of obscures and doesn't aid you in understanding. Hopefully, and I'm sure it will, and I'm sure you will agree, that you will know the basics of these attacks after listening to these presentations. So let's start by looking at the program header and having a bit of fun before we go deep. When you release anything to the market, you always hope that it will be useful to someone and not used for harmful purposes. In this case, I made a flippant comment, and as you well know, I'm prone to do that, about it'll probably help some graduate doing his MSc in information security. Well, look what arrived in the post. A few weeks later, a son of an old pal of mine found it on Packetstorm and was using it for his MSc project. I'm glad I could help. This is a little bit more ominous, but I had to keep it there because it was so complimentary. I did a search for the code to just cut and paste some of the examples into the presentation. I don't know if you're like me. I tend to do my development and my jobbing security work on a Linux-based machine, and I tend to a physical machine. I'm an old farty, and I tend to do all my presentations and all my reports and risk analysis on a nice Windows machine. So I was browsing simply for some source, and I found that someone had kindly pasted my code into Pastebin. Well, it made it easier for me to write the program. However, they were very complimentary. Apparently, it is both impressive and well done. So thank you, sir, for your kind comments. Now let's relate the attack to the C code. If you scroll through this code, you'll come to where we set up the spoof of the UDP packet. Now in Linux, to spoof a UDP packet, it's very simple. You have to put a UDP, an IP header structure in memory, and then you'll move the target address simply into that structure, and of course you'll put it into the appropriate format using the appropriate library call. However, here, if you just don't write it out as a raw socket, that will appear as data. So you have to write a raw socket, open a raw socket, and then you have to set a socket option to ensure that the header is included. If you don't do that, all that will happen is that you will send out an IP datagram probably a corrupt IP datagram, but you will send out an IP datagram with the facsimile of an IP data structure in it, and that won't go to the intended target. Now, in light of the HHH attack that we saw against the UDP port 53 in the previous presentation, and I guess my comments about DNS being a more complex protocol, and I do state this a couple of times in the book, and when you work through the examples in the book, I hope, in fact I know, you will agree. I just wanted to copy this bit of a subroutine out to exemplify that. Now, a DNS packet serves a number of different types of queries and response. Therefore it needs a packet type. It serves a number of different people, so therefore it needs a transaction ID. And that's critical when you need to understand DNS forgery, DNS cache poisoning. A DNS server can also provide authoritative or non-authoritative responses, and to make it non-authoritative you set a flag. So there are a number of flags that we need to set before it becomes a valid answerable DNS query. Key to this attack, we need to make sure that it's a recursive query, and we've covered that in depth in the book and a little bit in the previous slides. It's a query, and we can do a number of queries, so we have to make sure that this is represented. We only have one query, we have no answers because it's not a response, and at this stage we do not have an authoritative count. And then simply we move the query structures into the packet. Now these themselves are not simple, and in the next slide we will show you how even a simple dub in DNS has to be constructed with care. Now, to exemplify that fact, I've pulled out another portion of a subroutine from the code that you can find yourself that shows what a fully qualified DNS name will look like in a packet or in memory. If we take loudfatbloke, www.loud-fat-bloke.co.uk, to put it in the query info for a DNS request, we need to reformat it as 3 www, A for 10, loud fat bloke, 2 for CO, 2 for UK, and then behind that I've put the query type necessary to have a valid query. You can look out for that in the packet trace. So the techies amongst you really want to run it. We'll go through a packet dump quickly, and just a quick plug for the book where it has these details far more in depth for you to study and enjoy. Now, if you've got this far, you probably know what I'm doing now. For those that are brave and are diving into this kind of thing for the first time, I'm basically going to run a packet capture. I'm using the traditional program TCP dump that all us oldies believe is the best thing since sliced bread. I'm going to be running it on ETH0, that's my first Ethernet interface. I'm not going to do DNS lookups. I'm going to record every single byte of the packet, and I'm going to write the output to a file called DnsReflectedAttacks. But I'm only going to capture UDP packets that reference port 53. Now that's destination and source port 53. Then I run my favorite program, DNS-SP-Query. I'm going to run the program. I'm going to spoof the address to the classic RFC 1918 10.0.0.1. I'm going to my DNS server at this address, and I'm going to work with that URL. So here you'll see the output from the exploit. Obviously you would expect me to give a plug for the book. After all, it is for charity. Have I mentioned that? It shows the spoofed IP source address. It shows the destination server address, and it shows the fully qualified DSN name that we will be querying. Here it gives you a packet dump of the packet and various lengths, the overall length of the DNS query. When we rerun TCP dump, all you have to do is use this simple command, TCP dump -m, because we don't want to do DNS lookups. Tell it that we want to read the whole packet, -r is the read flag, and replay the file again. So here we can see the IP address, the destination IP address, and we can tell from that domain that's DNS port 53, and here we have that it's any query for the URI www.loudfatbloke.co.uk with a length of 47. Diving deeper, you can see that I've now run a TCP dump with a full hex and ASCII dump reading from the same file. So as before, we have it from the 10 class address 10.0.0.1 to my DNS server on 192.168.0.120 on UDP port 53. The ubiquitous 45 signifies to us that it is a IP version 4 packet with no IP options. Then we have the usual UDP header, and there you can see clearly what I mentioned before, the URI that's being queried. So we have the 3 www e loud fat bloke. At the back of the query we have the query type and the query class, and this is represented by the lines of code in DNS-SP-Query moving 255 into the structure QInfo with the member Q type, and likewise the query class being set to 1. Now I'm sure you want to know more, so buy the book. It's for charity. Now I know that you want to know why I've been talking like this, and the simple reason is I've been practicing my NLP and my Milton meta model for linguistics. I'm hoping to basically encourage you to buy the books. I personally find it incredibly irritating when people do it to me. So here's a word of apology. I must have been hanging with hackers for too long. And, by the way, if you start clucking like a chicken, it's got nothing to do with me. You've just lost it. Well, congratulations. You've made it through listening to my voice, the whole presentation. Give yourself a pat on the back. As I promised, I've given you the URL for the Sepsis Trust and ICU steps. Please donate. As part of this project, I'm not only writing the book, I've written a number of Android apps that hopefully people will find useful and therefore contribute. And also there's these YouTube videos. Sepsis and the aftermath of any prolonged ICU stay is a very a traumatic experience, and like I say, many people aren't as stubborn as me, and they literally have to give up work. More people are affected by it than those that than many of the cancers. Many people suffer post-traumatic stress. Over 16% of them suffer really severe post-traumatic stress, and that's just not acceptable in this day and age. So please donate. As I mentioned, there are Android apps out there that will be updated. There are more videos coming, and there's the book. So if you don't think any of that is of value, please just go straight to the Sepsis Trust and donate directly. Thank you very much. That's the book. These are the other items available as part of this program. And that's me. Thank you for your time.